Thanks very much for coming to this seminar today. It's a pleasure to introduce Kari, Principal Scientist at VTT Technical Research Center of Finland, who's just describing to me it's a joint government-sponsored, industry-sponsored research center. He is, I gather, well known to the ICE people here in Hanover, or somewhat well known. His PhD is from Helsinki University of Technology in Finland in the strengths of materials. He's been conducting research in nonlinear stability and optimization of thin-walled steel structures and modeling of high-temperature creep. He's recently focused on ice structure interaction, forces exerted on marine structures and ships, as well as ice-induced vibration of structures. He specializes in numerical simulations and the modeling of failure and fragmentation of brittle-like materials. He's an active member of national and international committees and associations to regulated to strengthen materials and ice research. Interestingly, if you read his bio, it's an active flamenco guitarist and Nordic skater. So very interesting. Today his talk will be engineering challenges related to the development of the Arctic, the Finnish perspective. So thank you very much for coming, and we look forward to your talk.
At first, I want to thank Professor Brian Hoku and Professor Renald Schulson for inviting me to be here. I'm glad to be here, and I was surprised that today I had a full program, and I have enjoyed discussions with your experts and students. It has been a pleasant day. So, my talk has three main topics. I start speaking with Arctic issues from the global perspective, and then speak something about, pick out some example of Arctic engineering interests from Finnish perspective, and finally I will speak shortly about ice forces and ice mechanics. But at first, I will tell a few facts about Finland. Finland is one of the 8 countries inside the polar circle. Our capital, Helsinki, is located at the same latitude as Anchorage, Alaska, but fortunately it is warmer. Our neighbors on the western side are Norway and Sweden, and on the eastern side there's Russia. But Sweden and Finland are different from other Arctic countries compared to, for example, Norway. Finland and Sweden, they don't have access to Arctic oceans, Arctic seas. So in that sense, it's quite different. The challenge in Northern Europe is that the Baltic Sea freezes during winter. The striped area is showing the Baltic Sea. So it means that ice conditions must be taken account when building offshore structures. But as you can see from these figures, it really varies how much ice there is in different years. But always the coastline of Finland is frozen and the northern part of the Baltic Sea. But luckily, Finns like ice and snow. So skating on sea ice, like in these pictures, is quite common. And snow, we like. Because of the ice cover, of course, all the ports freeze during winter. And that's a challenge because majority of Finnish import and export are passed by the Baltic Sea. Therefore, it's really important that all ports are kept open all year round. And so, for this reason, winter navigation, icebreakers, Arctic engineering has become important in Finland. And in fact, most of the icebreakers that are in service today in the world have been built in Finland or either designed in Finland. This video was shot about 100 years ago in Helsinki. This icebreaker Dartmouth arriving to Helsinki harbor. As you can see, the safety regulation in that time were different if there were. But the ship itself, it had steam engines, 4,000 horsepower, but the most important, it needed 4,000 kilograms coal per hour. So there were a lot of men shoveling coal to get it run. So global fleet of icebreakers is about 100, and to get the idea about the icebreakers in different countries, Finland has 8 icebreakers, and US, not 3, I heard in the discussion, but 1.5. Canada 8, and Russia 90. No, 40. Sorry. But there has been discussion that new icebreakers will be built for US Coast Guard. Yeah, so, good shot. The Arctic Council was established in 1996. It's an intergovernmental forum promoting cooperation and coordination among these 8 Arctic states. And currently, Finland is chairing the Arctic Council. At 2013, in the Arctic Council meeting in Sweden, things somehow changed. Arctic matters got more interest because there were 6 new permanent observers accepted to Arctic Council. Especially in interest of Russia and China has been increased. One reason for that interest is that according to US Geological Survey, more than 1/5 of undiscovered Arctic oil and gas is in the Arctic. And as the figures show, most of that is in Russian territory. So about half of undiscovered oil and gas is in Russian territory. So Russia is quite an important player in the Arctic because of the energy. And oil and gas is vital to the Russian economy. So it forms a remarkable share of Russian GDP, and in fact, natural gas imported to Europe, 1/3 of it comes from Russia. So it's important in export. But there's a challenge. According to researches I read, the western Siberian sources are slowly drying up, and therefore the new fields are needed, but the offshore fields are extremely difficult. So in order to access and exploit and deliver resources to markets, Russians has planned to invest Northern Sea route. And it means big investments to infrastructure, not only to ships, but also to ports, icebreakers, oil spill response, and different things. But in addition to that, there's also a growing security interest in Russia. So ballistic missile submarines are located in the Arctic area. China is also preparing to the opening of the Arctic sea routes. The Northern Sea route would shorten the shipping time from China to Europe, and what is important, it would provide a second alternative if there's some kind of crisis going on in Suez Canal. So the Northern Sea route would also give access to Russian hydrocarbon and perhaps to rich fishing areas in the Arctic. And what are the Chinese actions? China has been active in forming bilateral agreements with Arctic countries, and they have also invested a lot of national Arctic research. And they strongly promote international cooperation with Arctic countries, invite foreign researchers, organize seminars, etc. I myself was in China 1 year ago for 1 month. US attention to Arctic, I think it has been a bit limited. Arctic natural resources are not that important to US as they are, for example, to Russia. But there are also security issues for US because the global missile defense system is located in the Arctic. And also US is interested about the possible northern sea routes in the Arctic. And US has been a notable forerunner in the climate research. So that was the first part. So, about the Arctic interest from Finnish perspective. But one thing I want to point out is timescale related to opening of the Arctic. When I read newspapers, I easily get an impression that Arctic shipping routes will open pretty soon. But that is not the case. Based on estimation, based on global warming models, a rough estimate is that shipping season grows 1 week per 10 years. So after 40 years, we will have 1 month more shipping season. So time scale might be different than the impression we get from newspaper. The examples of Arctic technology interests from the Finnish perspective, first of all, is shipping and also offshore wind energy. And in shipping, there are 2 different things, polar cruises and the Northern Sea route. There's an increasing interest against polar cruising. Nowadays, there are 80 vessels in the market for these polar cruises, and they expect that the capacity will be increased by 40% within the next 2 years. The northern shipping route it's not just about the icebreakers. So to build up the sea route, you need a lot of more different kind of infrastructure, like I already mentioned, ports, oil spilling response, security centers, but also we should be able to know what are the ice conditions, to be able to do forecasting, ice forecasting, route planning, etc. So all the things have to be solved before starting the northern shipping route. But one thing I want to tell you about, this is about ship performance, because the idea, what I'm telling you about, is so simple, but it's so good. So, all vessels, icebreakers, they have to operate both in ice and both in open water. And the problem is that you should optimize both ice breaking capability and open water resistance. And that's not easy, but there's a simple solution. It's double acting ship. And it's based on the existing azimuthing propeller system. So propellers that you can rotate 180 degrees. There are a lot of these systems available, ABB, Rolls-Royce, Wärtsilä. The idea is that when our ship is going forward, when it is going on open water, and it's going backwards when it's breaking ice. So it has different shapes in backwards and forward. Isn't it simple? And what? And this system, it was proposed in Masayards, Finland, 1990, and patented. And it's a common practice in icebreakers today. This is the example of US Coast Guard Mackinac Great Lakes icebreaker. It has double acting ship. And this ship was developed jointly with US Coast Guard and Arctic, and model tests were done in Finland. The second thing I want to talk about is offshore wind power. It might be hard to believe that they are building wind power in ice-infested waters, but that is going on. And the reason in Europe, which I know better, is that onshore wind power has been saturated. Germans, UK, Denmark, people don't want no more windmills to my backyard. So the solution is to go offshore. And the challenge in offshore is that there are higher foundation costs. You could say that in Finnish coasts, the foundation costs are 3 times onshore because of the ice conditions. But on the other hand, there are better wind conditions and there's small space. Recent plans, if we think offshore wind power capacity in the world is 14 gigawatts, but Germany, Denmark, and Belgium, they have planned to build 60 gigawatt more. So it means thousands units of offshore wind power. And at least some of them will be built in Baltic Sea, which is, as I told, frozen now and then. So in Denmark, it's about 1 time in the 7 years. Sea is frozen. So it's a challenge. This year, the pilot wind farm was installed into west coast of Finland. 10 wind turbines, each 4.2 megawatts, and it's the first wind farm built into real severe ice conditions. But also in US, there are plans to build wind power. So there's an icebreaker pilot project, plan to build 6 3-megawatt wind turbines to Lake area. And the capacity of, based on wind conditions, the lake area is 50 gigawatts. Another place where they have planned a new wind power is China, Bohai Bay. They have planned to build 1 gigawatt, so it's 200 units, 100 to 200 units. And in China, the ice conditions are really challenging. because of the tide and wind, ice drift velocity can be up to 1.2 meters per second. And it's really, really challenging for ice engineers. So, the last part I'm speaking about challenges related to ice, and ice forces are in the focus. There are ice forces which are have to deal with ships, but I'm concentrating on the fixed structures. The first thing is to realize that sea ice is not a constant smooth layer of ice. There's always cracks, channels, open water, ice with different thickness, big and small flows, possibly multi-year ice, ridges, icebergs. But the important thing is that the sea ice is drifting, and it's drifting because of the current and wind. And if there's only wind, the velocity of ice, drift velocity is about 1 to 3% of wind speed. And when this drifting ice is in interaction with structure, there will be ice forces. But in addition to that, the different features forming because ice is moving. And the figure on the top is about compression ridge, which is formed when two ice sheets are driven towards each other. It's formed by flexural failure and crushing, and then ice is just piling up. It can pile up. In Baltic Sea, the biggest ridge that measured has been 30 meters. And the important thing is that at the first, the ridge is just a pile of ice. But then it starts to freeze, especially below the waterline, and it consolidates. And then it's a real challenge for ships, or if ridge is interacting with the structure, it's giving high forces. In the below, there's another feature. There are more and more features, like this finger rafting. And this is what it looked like close to Helsinki. Yeah. It's possible to switch off the lights. That's finger rafting of 5 centimeters of ice. This example of ice piling up close to capital Helsinki, sea ice, piling up 5 millimeters thick of ice. The key questions in design, as I mentioned before, is what is the total ice force and what are the local pressures. For the third and one of the most important questions is the ice-induced vibrations. The structure may start to vibrate because of the drifting ice. And vibration, we know that it will cause fatigue of structures. But another thing to be aware of is icing of structures. That's also a severe problem. That's a ship. So structures prone to ice loads are offshore, wind power units, lighthouses, bridge piers, oil platforms, etc. This is an example. We were doing measurements. This is a lighthouse in the Baltic Sea close to Swedish coast. And we were measuring ice forces. The lighthouse was covered by force measurement panels. We were measuring forces for about 5 winters. And this is showing what happens there. So this is a lighthouse, and you can see ice drifting against the lighthouse, it's breaking, and sometimes it might start to build up like this. And this is a vibration of lighthouse. I took the film so that I was holding camera against the rail. So I'm not shaking, but the lighthouse is shaking. So it's vibrating while ice is crushing into small and big crust particles. And the big challenge in the defining ice forces is that the ice force pattern, how it looks like, and the force level is a function of ice velocity and the structural properties, like stiffness of the structure. But the physics of interaction, it is not well known yet. So therefore, the force predictions given by ice expert scattered by Ben. That's pretty much. So it's quite evident that further research is needed. So I will shortly tell about the ice mechanics model, what I've been dealing with and working with. But let's look what ice is. This is a cross-section of sea ice. Ice is crystalline material. And if we look at the cross-section, you can see that on the top layer, it's crystalline granular ice, but the majority of ice is formed of columnar ice. And the column diameter is typically up to 50 millimeters. It can be higher, it depends on the thickness of ice. Ice can be considered as a material in high temperatures because it's so close to its melting temperature. So, temperature and grain diameter affect significantly on the behavior and strength of ice. And we know that ice can exhibit both ductile and brittle behavior. It is ductile when it is loaded slowly, and it's brittle when loaded at higher rate. The challenge is that the micromechanical behavior is not completely fully understood. Ductile behavior is maybe better understood, but the brittle behavior is not completely. But what we know that cracking in grain size scale is highly important in this process. But the second challenge in the determination of ice forces is that the force is a result of continuous breaking process. So it's not that we solve when the first crack starts, but we have to be able to solve crack initiation, propagation, formation of fragments, interaction of fragments with other fragments, with structure, with virgin ice. So the process itself is really difficult to simulate. And this process is going on and going on. I will introduce a model which can be used also in the simulations of ice failure. It's called sliding wing crack model. Some of you have heard about it already before. And the mechanism itself has been studied a lot of in Dartmouth College. The model connects range scale mechanism to macromechanical failure. And the so-called axial splitting failure mode is in the key role. So I will shortly describe the mechanism. Let's consider compression of granular ice. Under compression, the grain boundaries start to slide. And because of the sliding, crack will be formed. And the crack can be intergranular or intragranular. And the crack size is in the range of grain diameter. And let's now then look how the crack behaves. So under further compression, the faces of the crack slide, and after some sliding, at the ends of the sliding crack, the wings start to form. And after further compression, the wings grow and finally break the specimen. The key thing in this is that the frictional sliding, the friction between the crack faces, have an important role. And we know that friction is a function of temperature and sliding velocity. If we look at a specimen with several cracks, the same mechanism works. Initial cracks, they start to grow, and they coalesce and split the specimen, as illustrated in the figure of Ilescu's and Schulzen experiments. Well, this mechanism, I have a program using Abacus software, and this shows simulation of axial splitting failure mode when ice is failing in a brittle manner. Now, in general, results fit very well to the experiments. It predicts ice strength as a function of grain size and temperature. I will show you. These examples are from compression tests. The blue lines are test results, and the red triangles are test results. The model accounts variation in grain size. Therefore, there's also variation in the simulation results. And the variation in the simulations look similar to variation in tests. This is the simulation under tension. The red triangles are test results, simulation results, and the other ones are test results. And then under biaxial compression of columnar ice, in this case, red ones are test results and blue ones are simulation results. So it works well in the small scale, and I adopted in larger scale. This example shows simulation of ice structure interaction. The structure here you can see it's moving, it's compliant. Now it's stuck. which shows ice crushing against structure. And this is important. We know from the experiments and when ice is breaking, there are so-called high-pressure zones, which are changing places. And this model I can predict also those high-pressure zones, which designers are interested in. Well, that concludes my presentation. Thank you for your attention.